So for the first topic is based on mechanism. Okay, so be honest with you. So for the question you have right on the quiz, it's not just ask you the rate law for the overall reaction. Okay, so I have multiple statements. Okay, it's not that 1, 2, or 3, 4, not that type. It's just one choice. Okay, so one correct choice. That's what we're looking for, but still requires you know about the whole reaction in terms of right. What's the overall reaction? What's the rate law for the overall reaction? Which step is really determining step, right? Is there a catalyst? Is there intermediate? Okay, so all of this relative information involved in mechanism. Okay, so I have statements regarding each term I just mentioned. Also, I have involving molecularity just based on the elementary step was the molecularity. Okay, so we'll talk about those as well through this question. I know this question itself really just asking us about the rate law for the overall reaction, but we're going more than that. I hope you realize that every time a question I give you, an example question, but we're actually talking about everything around it, right? Okay, so and about it as well, right? So basically, should be a good review for this concept. Please, if you're still having trouble, and please pay attention. Okay, and then definitely after yesterday, I do see some confusions in terms of equilibrium, right? And then equilibrium constant, rate constant, it's starting to get a little confusing. Okay, so then as I always try to emphasize on, if you're certain with each term, then you will not be confused. Okay, so let's try to do that, right? So whatever term we're learning, and then make sure you're very certain about it. And so that's certain. I also suggest when you learn it, try to get to 100%. You go, I'm 100% sure about what this term is about. Okay, so that's a level we should require ourselves to have. Okay, back let's look into the first topic. Okay, so mechanism. Okay, so as we said, this is a proposed mechanism, right? So it's in theory, right? So people go, okay, I think for this overall reaction, okay, so even though the wording is the overall reaction, but you should recognize, right, for the reaction, right? So this reaction is your overall reaction. Okay, so that's your overall reaction. And then for this overall reaction, people propose these 3 steps. People say, okay, for this reaction, I think we'll take these 3 steps, then we'll have our overall reaction. Now think about it. If you add step 1, step 2, step 3, what should you get? If you add step 1, step 2, step 3 all together, what do you think we should have? Very good. We should have that overall reaction. Exactly. And so that's the whole idea. Right? So again, we know this is overall. Then if you have those steps adds up should equals overall. Okay, so that's just something as a basic understanding. So again, for this overall reaction, we're saying, hey, it's going to take these 3 steps. Okay, so these 3 steps we call them are the elementary steps. Okay, so those are our elementary steps. Okay, so now again, for this overall reaction, in order to figure out the rate law for it, okay, so the rate law for this overall reaction, so in general, or based on before this section, right? So the early chapter 12, if we're trying to determine the rate law for the overall reaction, what are we supposed to do? Just not talking about specifically about this question, based on the past experience, right? If you're trying to figure out the rate law for overall reaction, we're trying to not talking about the mechanism, right? So just in theory, or when you have an overall reaction, if you didn't get, you're not given with mechanism, what are we supposed to? How you can figure out rate law? How are you going to figure out a rate law for over, right? So you're going to go rate law equals to, right, for a certain reaction will be K times concentration of the reactants raised to the power, right? So then you have to use experimental data and to determine the reaction order, right? That's still true. But again, just for this question, that's, again, we don't have the information to do all those work, right? As the other type of question. Okay, now back over here. So we're trying to say, okay, if we have those proposed mechanisms, we can actually use the information from the mechanism from those elementary steps. Then we can now, in theory, try to derive the rate law for the overall reaction. So that's what this about. Okay, so and then at the end of the day, after you derive the rate law for the overall reaction based on the mechanism, that rate law will equals to, or only it can be validated for the mechanism is that your rate law you derive based on the mechanism needs to match or needs to equal to the observed overall rate law. Is that clear? Okay, so at the end that this should match experimental data. Okay, so that's the story. Okay, so now we're trying to go by theory. Okay, so in theory, based on these 3 steps, we should be able to also derive it. Okay, so then if that's a story, okay, so how are you going to derive the rate law? How is the mechanism related to the overall rate law? Okay, so that will be the next question. And then I see people are answering my question, all right, for this question, right? So how do you determine the overall rate law based on the mechanism, based on the elementary steps, which is direct, right? So the direct relationship is what? So for based on mechanism, okay, so when you have mechanism, okay, so this is the key, right? So this key sentence everyone should know, okay? So the rate law for the overall reaction, the rate law for the overall reaction is basically determined by what? Is determined by, very good, the slow step. Okay, determined by the slow step. We also call it, I also saw people, right, typing it RDS, rate determining step. Okay, so that you also should, again, during quizzes or exam, if I just use abbreviation RDS, we all should know what that represents, right? We should go, well, what's that? Okay, it's a typo. Okay, no, it's rate determining step, which refers to the slowest step. Okay, so that's the bottleneck, right? Okay, so as I said, that's the traffic on your way home. That's what's determining how long it's gonna take you to go home on that day, right? Okay, or how long that hourglass is going to go, right? So of course, right? So that bottleneck, that's what hinders the whole overall rate, how fast, right? So remember in chapter 12, we're still talking about how fast the reaction goes. Okay, so that when it's slow, that means that's the trouble portion of that reaction, right? Okay, so back over here, if we understand this, okay, so then let's see, we are looking for the rate law for the overall reaction, okay, and then we know we should actually just now from this sentence we talk about, we know we have to go to the slow step. Okay, so then you go, now this is easy. If I understand my overall rate law for the rate law for my overall reaction should just equals to the rate law for the slow step. And I know for the elementary step, such as for step 2, what's the rate law should for it? Okay, what's the rate law should be for step 2, the slow step. Slow step also we can use RDS to refer it. Okay, so what's the rate law for it for this step? Do I have to do experiment? For elementary steps, no, we don't need, again, this is proposed, right? And then for this step, sometimes these certain steps are very short. The lifetime is really short. Okay, so then sometimes it's hard to really get the evidence, but people are trying, right? So trying to propose mechanism and prove it. Okay, but anyway, so we can just simply look at the reaction equation, use the coefficients. Okay, so that's the only time actually you can do that directly. Okay, so when you look at the elementary steps, the rate law for it should be just K times the concentration of Cl times the concentration CHCl3. That's all. Okay, and right? Right, products over reactants. I see. That's what I'm saying, right? So, right, think about it. We are dealing with chapter 12. We're not talking about equilibrium constant. We're talking about rate constant. Okay, so be careful with this. Okay, so we're talking about low, right, rate constant, and then we're representing rate law for it. Okay, so now about equilibrium, 2 terms. Okay, so back over here. So this should be, then you go, am I done? If you say the rate law for the slow step should really just equals to the rate law, this should be the rate law for the overall reaction. Then you say, essentially, I'm done. Okay, essentially, it's true. Okay, however, if this is the first step, if first step is slow step, you are really just done because that's a step is hinders, right? What's determined the overall reaction, and then that you're done. Okay, so that's very easy. But in this case, we are done, but not only because if you look at this, you have Cl. Okay, and then Cl, look at it. Is Cl even in the overall reaction at all? No, you can write Cl, it's not there at all. Okay, so it's not, right? Okay, so it's not even in the overall reaction. Okay, so then what should we do? Like I keep on saying, can you use something not even in the reaction to represent the rate law for it? Then how you can find out the concentration of it to do the whole calculation? Can we do that? No, right? Okay, so then the whole idea is not even in the overall reaction. We need to swap it out. We need to replace it. Okay, so then you need to replace this. Okay, then the way to replace this, and then you can look at the previous step. The previous step, you do have Cl involved, okay? And the previous step is a very fast step and reversible. Okay, so what does that mean? If I say the first step is reversible, now related to something we learned in chapter 13. Right? So if we say reaction happens fast and is reversible, that means the reaction will reach equilibrium. And at equilibrium, what happens? The rate for the forward reaction equals the rate of the reverse reaction. Okay, so that's what we use the information there for. Okay, so then now, right, if we understand that, so look at this. This arrow, essentially I should use double head arrow because we know reach equilibrium, and the double head arrow means the reaction will reach equilibrium. Okay, so that's particular. Okay, so we'll have to use that double head arrow for that information. Okay, so if you're saying, okay, my reaction is reversible or will reach equilibrium, then you have to use that double head arrow. Means the reaction will go forward and also will go reverse way. Okay, so now let me ask you, do you think other reaction always will have both ways? I know so far we go in chapter 13, other reaction we've mentioned, they're all equilibrium. No, right? Okay, so there's some reactions will be just forward, favors the forward direction. They go to completion to the product set, and that's it. Okay, so it doesn't go the reverse way. Okay, so we have to also not get limited by chapters, right, content. Okay, so anyway, so back here we understand, right? So that's equilibrium, and then I'll say the forward direction, the rate constant, I give it a notation, right, as K1, okay? And then reverse is K -1, because also people are asking me, okay, so where the -1, it just simply means it's reverse, so that's how we do a K -1, okay? If you like, you can use K to represent it, just a constant at the end of the day, right? Okay, so and also doesn't necessarily mean K1 has a negative relationship with K -1. No, really, it just whatever the rate constant for that forward direction, what's the rate constant for the reverse direction? Is that clear? Okay, so that's just a notation, that's all. Okay, so now I have those info again for based on for step 1, since it's reversible, which means we'll reach equilibrium. So I have this equal relationship, right? So rate of forward reaction equals to the rate of reverse reaction. Okay, and then now I'll like ask someone to help me to write down the rate law for the forward direction for step 1. Okay, who wants to volunteer? You have the power to turn on your mic if okay, or you're already telling me the answer. That's awesome too. Okay, so for the forward direction, okay, so we're looking at this. For the forward direction, how do you look at it? You're gonna look, what's the forward direction? For the first direction, if I asked you to only write the forward direction, what are you gonna give me? Right, for the first direction, if I ask you to only give me forward direction, right? So then you're gonna have Cl2 is having the rate constant K1 and giving you 2Cl. That's forward direction. That's direction goes, right? Okay, and then there's an elementary step. So quickly you can write down the rate law for it. That'll be K1 times the concentration of Cl2. That's it, right? So that's a forward direction. Okay, and what's the reverse direction? If I only write down the reversed for direction, now you see the point, right? So then what's the reverse? Now I have 2Cl, it's generating Cl2 for me. Okay, so that reverse direction, I have the rate constant as K-1. Okay, so then therefore the rate law for that step, I simply do the same thing. Rate law equals what? Rate constant times the concentration of the reactants. And if there's a coefficient, now you can raise to that power, because again, we're looking at the elementary step. That's what's allowed to do for elementary step. Okay, so then you can raise the power of 2, okay, because of the coefficient right over there too. Okay, so now you have this equal relationship. You go, wait a minute, why are we doing this? I want to ask you that. This is the key. You have to know why you're doing certain step. Do not just simply follow the step. That's not the point at all, right? Okay, so the point is why we're doing this. Okay, such as when we go home, why we're turning left here, right? Because we know we turn left here, next time we turn right, then we go home. Okay, so why we're doing this step? Very good, because the whole idea we're doing this to replace the Cl, right? Remember, that was the problem. We need to replace that. Okay, so and then we find out in this expression we have a Cl, we can isolate it and then swap it, then we get to the purpose where the whole point we're doing this, all of this work. Is that clear? Okay, so that's for that. And then now, if you're still remember, that's why we're setting up this relationship. And then you also will realize we will need to isolate Cl by itself. Okay, so isolating it, so that should be easy. This is really just math, right? So you're gonna divide the constant on both sides, and you have concentration times Cl2, and then this is squared. Okay, so now you go, okay, I have Cl, can I just use it? Not really. Okay, so if it's squared, that's different from just by itself. Okay, so then you have to get to just concentration of Cl by itself. How do we get that point? Square root. Okay, so we're gonna do square root on both sides. Okay, and then that's why we can get the concentration of Cl by itself, and then we have everything under the square root. Okay, so that's all you have. Okay, so come to this point now. Remember, the whole idea or the whole point doing this is now you can use that, which is this whole bunch, put that into this equation, and then we should be done. Okay, so because that will, again, that's why we're doing all of these steps for. Okay, I'm gonna add a page. Okay, so I'm gonna need some more space. Let me grab this equation. Okay, so that's the equation. I'm also gonna grab the other ones, don't worry. Okay, so then the other one is this one we just derived. Okay, so now we just need to plug that in there to put that in here. Okay, so let's do that together. Okay, so now that should be easy. So that rate law, remember, this expression is for slow step, but we also agree that should be for the overall reaction. Okay, so essentially after you're done with this step, we should be done. Okay, so then this will be equals to K, okay, and times this bunch. Let's just put this bunch in. Okay, times the concentration of CHCl3. Okay, so then you go, okay, so don't see a matching choice, or essentially for this question, I don't have a choice, so you go, that should be fine. Okay, I can report anything if I think that, like, as long as that makes sense. Okay, but if it's just I give you a more organized or more neat expression, what we're gonna do. Okay, so then let's also try to express the rate constant. Okay, so the rate constant, let's look at it. Okay, so you have K, and this under square root, essentially you can express it as K1 over K negative 1 square root also is the same thing as raised to the power of 1/2. I hope everyone understand that as well. Okay, so that's what we have. And then the concentration of Cl2 times 1/2, then you times the concentration of CHCl3. Okay, and then to make this into a neater formatting is that all that I circled up, right? It's all just constants. Okay, so you can essentially use just a K, where I'm gonna use, I don't know, K, I'll say K overall. Okay, so I'll say I have a K overall, whatever you wanted to label it, just a constant, right? If you have the particular numbers, you can plug them in, you get a number, right? So K, again, constant is what, just a value, right? Okay, so then you have a number and then just have everything else like what we just did. Okay, so now this should be the overall rate law. And then now let's grab it. Let's check it out. Here you go. Do I have everything from my overall reaction? Is it okay for me to use it to express my overall reaction? Let's look at it. Okay, so Cl2, yes, it's in my overall reaction as one of the reactants. CHCl3 is also as one of my reactants. Okay, looks logical, right? It's good, and I'm done. Okay, so because I'm not using something not even overall reaction to represent my reaction. Okay, so this is for that. Okay, so this is how you do the derivation process for when you have the first step as the slow step, as the fast step. Okay, the second step is slow step. Now think about this. Do we even need to look at the step 3? Do we even need to look at it for this particular question? Do we need it for looking for the overall reaction? Not really, right? Because again, you understand the key is the slow step. Okay, so we really just needed that. Okay.
Professor?
Yes.
Isn't there an easier step if you just take out the C, because there's one CL on the bottom and then on top there's two CL. You just take out the CL from the bottom and then on the top you'd be left with one CL. And then you could just take half of CL2. And then that'll be concentration of Cl2 to the power of half, and then that multiplied by that concentration of CHCl3 to get the rate law.
Wait because I wasn't following.
Because you're like, for step 2, like there's one Cl, right? And then on top there's two Cl. Don't you just take out that Cl, and then from the two Cl you take out one Cl?
How do you just take it out like that? How are you gonna take out?
Because like, isn't it because it's there's a reactant and it's product on top?
You're adding the equations?
I don't know, because I learned this on like class prep, so it was just like it showed me a different method of doing this. So
okay, based on what concept? Why you're doing that?
I'm not even sure, but it just told me that it's like some concept like that where you just take it out, and then since you took out one Cl, you just take half of Cl2. But it's okay, no problem. You can just continue.
I so that's right. That's you're playing with math, but then you have to understand, right? When you do things, you have to have a foundation. Why I'm doing that step, right? That's what's really important, right? So yes, for this question, that works out. What if I don't have that, and then how are you gonna do it based on what you're gonna do? Use what method to solve for it, right?
I've actually tried on multiple different ones that never worked every time I did it.
Right? Did you follow the steps or just taking for solving this?
No, I didn't follow your steps, but I followed their steps, and there was like literally 2 steps. Not even 2 steps, it was like 1 step thing, and you did it, and this literally give you the right answer that you're getting.
But to me, I don't think that's the point, right? What if I change the question? You can now follow that 2 steps, then what are you gonna do? you know what I'm saying? Is if the numbers doesn't, right? Not just simply you just do a half whatever the way. But anyway, so I personally do suggest you really understand the concepts why you're doing each step. That's, at least from my perspective, that's what we're learning here. But anyway, so
wait, sorry, Dr. Lau, can I ask a quick question?
Yes.
Would it be possible to have like 2 first fast steps and the last one be slow? Would you just do like the same kind of thing, taking the intermediate? Or
yeah, that'll be more complicated, right?
Okay.
Then that could be for certain more complicated mechanism, but then for our, in terms of quizzes or exam wise, we'll not go that far. Yeah.
Okay. Thank you.
Yeah, you're welcome. Okay, so back over here, if you have this situation, right, this is the math situation you have to do, right? So you have to understand the first step is reaching equilibrium, and then you have to do what we just talked about. Okay, and then if it's the first step is slow step, what do you think? If I have the first step is slow step already, we should be very happy, right? Because first step, solve the whole problem, we're done. Okay, so then that's what's important. Okay, so now let's think about the molecularity. Okay, so I mentioned I will ask you things like that. Okay, so if I say the molecularity for the rate determining step is unimolecular, what do you say? Is my statement true or it's false? I said the rate determining step right? For the molecularity is unimolecular. That's false because you have to understand which step is rate determining step, right? Okay. And then speaking of which, you're talking about clutch. I don't know if any, right? I heard from our classmates, right? So if you're receiving, they reach out to you claiming I told them or is associated with me, just to clarify, I'm not associated with that resource at all. And yes, they do have my information. That's because all my syllabus is to public. Whoever can come to our department's website, they can get my syllabus. They can use the info to claim it's for our class, but now in terms of if you wanted to watch it to learn the material, that's fine. But if you're thinking whatever the practice they give you should be mimicking the exam, that's totally not true. Again, I don't even know what they put up there. I'm not associated at all, just to clarify. Okay. But anyway, so back over here, right? So for the elementary step, you just need to see how many molecules are there on the right-hand side. Okay, so that's how simply you're going to decide the molecularity. Okay, so then over here, for the rate determining step, is a slow step. Okay, and then that's bimolecular. It's fine if you think it's helpful. I have nothing against it. I'm just saying if you think that should be, it should be mimicking my exam. Then you go, exam is nothing like those practice. That's not right. I'm not associated with that. Okay, so it's fine. You can use it. That's okay. Okay, so that's rate determining step will be bimolecular. Okay, and for the first step is what? It's just one molecule on the record side, right? So that will be just unimolecular. Okay, what if I have this? What if I have a step? I'm just making things up. What if I have a step like this? Okay, so I have my step like that. What's the molecularity? Right, that's bi, because literally I can write down as 2Cl. I can also write this, right, as Cl plus Cl. You also see each way, either way, that's telling you bi, right? Okay, so that's something you have to be recognized. Okay, do not just see, okay, just Cl, just one type of thing. No, we're talking about how many quantity wise. Okay, so even you can have two same thing or two different things. That's we're counting the total quantity of it. Okay, so that's for that. Okay, and intermediate. What's defined as an intermediate? Cl, very good. Okay, Cl is intermediate. How do you say it again by definition? Is it in the reactants? Is it there in the very beginning? No, right? Okay, so where is gonna start to show up? It's gonna show up after, right? You're gonna produce it first through your reaction, then you use it right away. And it's not even in the overall reaction at the end either, right? Okay, so that's what intermediate. Okay, so and then what's the catalyst? Not basing off this reaction, just it's not there. Yeah, if you're trying to recognize a catalyst, what's the concept you will need to know to use it to recognize a catalyst, right? It will be initially in the reaction and also will be in there as part of the product. Okay, so throughout the process, you're gonna being consumed, very good, then you're gonna reproduce it. Okay, so that's what catalyst is. And then also very true, it's gonna help speed up the reaction, right? So make the reaction goes faster. Okay, so and then by providing a alternative mechanism. Okay, so that's what catalyst is. Okay, so again, this question I asked you from different angles and I cover all the basic definitions. Okay, so that those are always should be the key to help you. Yes, go ahead.
I had a question. So you know how you when we find the intermediate, which is the Cl, so you circled one in step 1 and step 2. So would the step 3 one count as well?
Yes, right. For this 2Cl we produce in the first step, you use one in the second step, you use the other one on the third step, and then that's all done. We use them all through the whole elementary steps. So that's for the first question. Okay, so now let's look at the next one. Okay, so now if we're talking about Kp, which chapter are we at? What's this Kp represent? Right, that's also something we have to be very clear about. Chapter 13. We're talking about equilibrium constant. Okay, so very good. Okay, so now we're talking about equilibrium constant. And then by the way, okay, so I also got emails about, the when we talk about in chapter 13, we're trying to, right? So we say when we express equilibrium constant, we don't even look at pure solid or pure liquid because the concentrations for them do not change. They stay constant, therefore they're not affecting the equilibrium constant. Okay, so that's what we said in chapter 13. And then I have been emphasizing on that multiple times, right? Okay, and then think about this. When you're dealing with rate constant, where you're calculating rate law in chapter 12, do you need to pay attention to solid liquid? Are you going to take solid liquid out? No, right? Okay, so do not get confused. In chapter 12, solid liquid, they're just regular reactants and products. You needed to use them for your calculation. And actually, for chapter 12, mostly we're looking into reactants, right? So of course, in certain definition, you do use products, but like rate law or for the integrated rate law, those are just involving reactants, right? Okay, so these are the things should be able to differentiate. Okay, and then right? Okay, so now let's look at equilibrium constant. Okay, so equilibrium constant, this is Kp. And I see people asking, what's the difference between Kp and Kc? I see very good. You tell the right relationship. Because they're related, so they're different. How different? What P represents? Kp, we're calculating. P just represents pressure. Kc, C just represents concentration. Right? Okay, so that's the difference, right? So either you're expressing the equilibrium constant based on concentrations, or you express equilibrium constant based on pressure. That's the difference, right? And then how they're related is Fatima give the equation, right? So that's the equation you can use to the calculation. But actually for today, I didn't test you that, right? That's what we just learned yesterday. You're sad, you wanted me to test you? You're ready for the equation? But I will test you on the exam, so don't be sad. I will test you on the exam, don't worry. Okay, so that's for that. So now let's look at this. For this question, okay, so now let's start to rate it. I give you the Kp value, okay, and then you're given with an equilibrium mixture, okay. So equilibrium mixture. Now, that what do you think these values are? If I ask you to be more specific, those are P, the pressure of carbon monoxide at equilibrium, right? At equilibrium, and this the other number is also the partial pressure for chlorine at equilibrium. Okay, so that's just something you have to be very clear, because you also realize, like the questions we dealt with yesterday, right? So I could give you initial partial pressures, and then give you some more information that you have to set up ice table to solve those type of questions. But if certain question didn't really mention initial, then you should go, this question should be easy because I'm already given the information at equilibrium. I can just already use it. Is that clear? There's also ability you need to have for identify what question you're really calculating, because during the exam, right? So you have to be quickly recognize what's the type of question you're dealing with. Okay, so if everything mentioned just for equilibrium, you're also calculating something at equilibrium, go, that's easy because I should have most information given. Okay, so then if you go, you know that, and then look at the questions asking you for partial pressure, it's also at equilibrium, because again, you're looking into an equilibrium mixture. Everything is at equilibrium. Okay, so now that's what you know we're looking for. Then, as always, right, the thought process will be, if we're talking about Kp, let's express it. Okay, so now then how do we express equilibrium constant in terms of pressure? Kp. How do we express this? What do we do? Right, so we're gonna use, now is the time to use products over reactants. Okay, so now that's what that is. Okay, so products will be COCl2, I'm sorry, not concentration, we're doing pressure. Okay, so pressure raised to the power of 1, because the coefficient is 1. Okay, and then if I have other coefficients such as 2 or 3, what are you gonna do? You're gonna raise to that power. Okay, so that's for that, and then go over partial pressure of CO raised to the power of 1, partial pressure of Cl2 raised to the power of 1. Again, every pressure should be the pressure at equilibrium. Okay, and then again, the question is directly giving us those information. Okay, so now the next thing, we just need to plug in the values and finish up the calculation. Okay, so this will be, we know we're looking for this. We know the other two. Okay, I'm just gonna do squared. You understand why I'm doing that, because the same concentration. Okay, so I just to save some space. Okay, so that's why I just did that for. Okay, so that's what I have, and this equals to 1.49 times 10 to the power 8. So now we just simply need to solve for this question. Okay, I have the answer. Let me see what's the end. Very good. I'm sorry. This, the partial pressure will be 7.34 A. Very good. Okay, so that's what how you're gonna solve this type of question. Okay, so for today, all easy question, but you have to have the ability to recognize when you have an easy question, when you have the ice table to set up. Okay, today you don't have ice table because, right, just because the contents for today. Is this clear? Okay, so you have a similar question like this, calculating based on pressure, very easy. Okay, the same old steps, and you should be able to do it. Okay, so that's for that. Now let's look at the next question. I ask you to write the equilibrium constant for the following reaction. So let's do Kc. Okay, if I ask you to express Kc for this reaction, very good. The first thing you should recognize, this is a heterogeneous. Okay, so let me see, how do you spell it? Heterogeneous. Okay, equilibrium. Okay, so that's what I have. Okay, so which means you have to, first thing first, you have to look at solid. I'm not even looking at it. Okay, so it's because the constant, I mean, the concentration will stay constant, not affecting my equilibrium constant. So now I just need to express it with products over reactants, and that'll be the concentration of CO2 over concentration of CO. Then you're done, right? So this is how easy that will be. Again, what if, right? I give you, just say for this, I give you more information. What if? Okay, so I said, okay, the concentration for CO2 at equilibrium is 0.12, whatever. Okay, I give you some concentration of CO, which will be this. Okay, and I ask you to calculate, right? So think about this. If you didn't recognize solids are now more involved, or I can give you a number. I say, okay, the concentration of iron outside is something. I can be a tricky like this. I give you info. Are you even going to use those for the solid? No, right? Or you could be, or sometimes if I didn't give you the info, but I give you a choice, more information is needed, right? If you didn't know this is a heterogeneous, then you go, I don't have all the concentration. I can now calculate. So then you're going to choose that. So don't get confused, because at the end of the day, you need to know what's important. This is the testing points. It's a heterogeneous. You're not looking at a solid. Either I give you the info, you're not going to use it, or I didn't give you the info, you just don't need to worry about it anyway. Those I assumed, right? I give a random number. It's not, I just give a random value to address on some points. Okay, so that's for that. And then let's look at the next one. Okay, the next one, again, right? If I mention equilibrium constant, you know you're dealing with equilibrium, which is chapter 13. Okay, so first thing first, you can look at the system. I'll just guess this involved. Okay, so you go, okay, so that's good. Everything should be related to the calculation or related to equilibrium constant. And then the thing is, the question is just straightforwardly telling you KEQ equals to 50 at 25 degrees Celsius and say at equilibrium. Okay, and then what do we have? Okay, so then what are you comparing with? Okay, so that will be it. Okay, so very good. At equilibrium, you are thinking about K, and then in order to determine at equilibrium, which way direction favored. Okay, so then you're going to compare with 1. Okay, so the reason for this, think about it, explains this already during the lecture, right? So K equals to what? Very general, in general, the format is products to whatever power to the coefficients over reactants. Okay, so now think about why we chose that value 1 to compare with. Okay, so if I say K equals to 1, think about it, what it really means. Look at the expression. If I say K equals to 1, what do you think it means? In your beaker, right? At equilibrium in your beaker, what do you have more? Approximately equal. You probably have similar concentration between the reactants and products. Look at that expression. That's what it means, right? Okay, and then that's the reason why we're asking you at equilibrium, what do you have more in that reaction? You're going to compare with 1. Okay, so that's the whole reason. Okay, so then you go, what about Q? Is this question anything to do with Q? What is this question anything to do with Q? What's Q? You go, I remember there's a comparison with Q, but there's nothing to do with Q. Q is at any moment in this situation, Q just K, because we're at equilibrium. That's why I'm trying to emphasize on this, right? So you're already at equilibrium. Think about, as I use example, you're already in coastal. We don't have to determine if we're on our way to coastal or past coastal. Where are they there? That's what we're looking into. It's nothing to do. You don't have to determine where are you at anymore. You know where you are exactly. Is this clear? Okay, you know you're at equilibrium, and we're trying to say at equilibrium, what do you have more in this reaction? Okay, so then you see now the reason, that's why we're comparing K with 1. Okay, so if K is bigger than 1, what do I have in the beaker? Look at this mathematical relationship. If it's bigger than 1, what does that mean? Which is more? Product is going to be more. Okay, so look at this definition. That explains everything, right? Okay, so then when K bigger than 1, you have more products. If it's K smaller than 1, you have more reactants. If it's K about equals to 1, you probably similar amount of both, right? Okay, so again, the whole thing is at equilibrium. That's already certain. It's at equilibrium. Either you have K bigger than 1, you have more products, or you have K smaller than 1, you have more reactants. No matter what, all of them, we are only talking about at equilibrium. Everything is at equilibrium no matter what. Okay, so that's something we have to be very clear. Are we good? Right, we are at equilibrium. That's the condition. That's what we're looking at. Okay, so is it 1K equals to 0? Only reactants are present. That's true. Very true. Very good thinking. If you have K equals to 0, only reactants, the reaction will have to go to the product side. That's probably not at equilibrium, don't you think? Right? K equals to 0, then that's probably not at equilibrium. Right? If it's at equilibrium, Fatima, right? Very good question, but we're thinking about this, right? At equilibrium, what do we say? Reaction goes both ways, right? If it's at 0, reaction has to go to forward direction, right? Then it shouldn't be at equilibrium. Very good, right? Okay, so that's for that. Okay, and then this is what this question is about. Okay, so now you only need to be able to recognize the number, right? So I have 50. 50 is bigger than 1. What do we say, right? You have more of the products. Okay, so this type of question should be super duper easy. You read it, you know what's this about. 5 seconds, we know the answer, right? Okay, 5 seconds, I think it's too long, right? Probably 2 seconds. You read the number, we clearly see what's the relationship between 1 and the number, then we know the answer. Okay, what if I give you a value like this? Sometimes I see people have confusion like this. I have 5.2 times 10 to the power negative 7. What this value? Is it bigger than 1, smaller than 1, less than 1? Is this number a negative value? Is this number negative? No, right? Okay, so don't get confused because sometimes people think it's negative. Again, for equilibrium constant, it's always positive, period. Okay, and then for this value is what? Is you have 7 zeros up front. That's what this center notation just equals to what I just wrote out, right? The number is very tiny, very small, but still bigger than 1, smaller. I mean, still bigger than 0, smaller than 1. That's what that number is, right? Okay, so now you have this question, and now let's look at the last one, then you're ready to go. Okay, so the last question I have, today I actually have 6 questions, okay, 6 questions on your quiz, okay? So the last one is, I pretty much have 2 questions, right? Like on Q, I have 1 question on Q, I have 1 question you have to calculate Q and compare with K, okay? But anyway, so you will see, okay? So now let's look at this question. You have this equilibrium, and you have Kc value given, and you say the concentration of H2 and H2S is that many moles and that many moles in 2 liter, okay? And then asking you to express Q and calculate it, reaction quotient. Okay, so how do you express Q? First thing first, QC will equals to products over reactants, right? Okay, so H2S over H2 times S. Is this true? Is this a true expression? No. What's the problem, right? This sulfur is not involved because it's a solid, right? Okay, so this should be the quotient, the reaction quotient expression. Okay, now look, right? You expressing it is concentration over concentration. Now read the info. I give you the many moles in 2 liter. We have to deal with this. I have a question. I did give you moles and liter. You have to do a calculation. Otherwise, you never get to the correct answer. Okay, so you are using molarity. If that's not given directly, you have to calculate for it. Okay, so therefore, the concentration for H2S and H2 should be what? Okay, so let's do H2 first. Okay, for hydrogen, given moles is 0.32 mole divided by 2 liter. That's easy, right? 0.16 molarity. And now the other one will be 0.28 divided by 2. So I have 0.14 molarity. Okay, so now you have the concentrations. Now we can plug them in. Okay, so you can plug them in. And then in this case, really, you division-wise will be fine. But what if I had exponents? Then they're going to mess everything up. Okay, so if you go, I also get to the same answer. Okay, H2S, what's the concentration? Who got 1.143, Christine? It shouldn't be products over reactants. Products is what? 0.14, isn't it? Right, over 0.116. Right? What should we get? Okay, be careful with that, okay? What are we getting? Very good, 0.875. Okay, that's what we should have. Okay, over products over reactants. Okay, so that's the QC. Now you did a calculation. Okay, so now if I ask you which direction gonna go, okay, so now think about how are you gonna determine that? Okay, so how are you gonna determine that? Think about it. This Q, or this concentration you calculated, where are we? Where are we? That's the question. Did the question say we're at equilibrium? No, you have to determine where you are. That's the problem. The previous question, the question said we are at equilibrium already. Okay, this question you have to decide where are you? Is this reaction at equilibrium? Is it right? Is it have to go reverse way, or is it going forward way, or is at? That's something you have to decide for this question. Okay, exactly where we passed it. Let's see. Okay, so now let's see, we need to compare Kc and Qc. For this type of question, you have to determine which way reaction goes. Okay, so then therefore, when you do the comparison, Qc is 0.875, Kc is essentially this number, right? So you compare these two. Which one's bigger? Qc is bigger than Kc, so which means you passed, right? So basically, at this moment, you have more of the products. It's gonna go reverse way to reach equilibrium, to that equilibrium, which should be this value. Okay, so when Qc is bigger than Kc, the reaction goes to the left, go to left or reverse, whatever the words you want to use. Okay, so this is the problem. Okay, so this question, you don't know where you're at. You have to decide which way to go. And then for the previous question, you know exactly where you are. You need to decide in that at that moment, at equilibrium, what do you have more? Those are 2 totally different concepts, okay, 2 different situations. So make sure you're clear about all of this. Okay, so today, essentially a very easy questions, but lots of concepts you need to be clear about. Is this good? Okay, so that's everything actually for today. I believe you all should be able to do a good job. Okay, and then looking forward to it. And then study, I have to say, as always, study during the weekend, and then see you next Monday. Why is going to the left? Okay, so when you have QC is bigger than Kc, that means the reaction has to go to the reverse way because it already passed that equilibrium. So you actually have more of the products, and then that's now the equilibrium. Now everyone's happy in a way if you want to think about it, right? So it has to go the reverse way. So why don't we compare to 1 all the time? Right? K compared to 1, as I just explained, you only compare to 1 because it's at equilibrium, and then you want to see what's more in that at that moment, right? And then if you're trying to determine which way it goes, you have to compare that moment to where you're supposed to go. Like I said, Costco, right? If you're in Costco, you just need to worry about what's in Costco. But now we're not talking about where are I in Costco. We're saying, are we at Costco or we past Costco? What are we supposed to do, right? So that's for that. Okay, so two different things. For question 5, we do not have to worry about, no, nothing to do with it. The temperature is just to be more scientific in terms of then those numbers is supposed to come matching with that temperature because temperature is sensitive, right? So it's going to affect equilibrium constant as we already talked about yesterday. Yeah, okay. So this is everything for today.